At its core, reinforcement learning reduces the entire problem of sequential decision-making to a single objective. Whether navigating traffic or a robotic arm sorting materials, the agent maximizes one specific thing: cumulative reward over time, the return, or G sub t. To calculate that expected return, agents rely on value functions. These functions act as a mathematical map, assigning a specific numerical value to being in a certain state, or taking a certain action from that state, based on the long-term reward the agent can expect to collect by following its current policy. If an engineer knows exactly how an environment will behave, meaning they have the exact state transition probability function, they can calculate the optimal policy directly. They do this using the Bellman expectation equation. It evaluates the value of a state by looking at the immediate reward plus the discounted value of all possible future states, weighted by the exact probability of those transitions occurring. But in highly complex physical systems, like a multi-jointed industrial robotic manipulator dealing with friction, payload variances, and sensor noise, possessing a perfect mathematical model of the environment is virtually impossible. Without that exact transition probability function, the traditional dynamic programming methods that rely on the Bellman equations hit a dead end. The math requires certainty, and reality rarely provides it. This lack of a perfect model forces a specific engineering shift. Instead of using model-based planning to calculate solutions in advance, agents must transition to model-free learning. They must deduce the value of their actions purely from raw, unmapped experience. The most direct method for an agent to evaluate a policy without an environmental model is simply to test it and measure the result. This is the Monte Carlo method. Monte Carlo works by having the agent follow its current policy to the absolute end of an episode. It records the true cumulative return of that complete sequence, and then mathematically averages those returns over time to estimate the value of the states it visited. Depending on the specific architecture, engineers configure this averaging process differently. First Visit Monte Carlo calculates the average based only on the initial time an agent lands on a state during an episode. Every Visit Monte Carlo includes the returns following every single time that state is crossed. Because it relies on averaging complete returns, Monte Carlo carries a strict mathematical requirement. An episode must definitively terminate before any value function updates can occur. For continuous tasks like network routing or traffic control that never actually stop, this requirement is a bottleneck. It is also a liability in physical systems, where waiting to learn from a failure means crashing an expensive robot. Monte Carlo provides empirical, unbiased data, but its inability to update estimates on the fly creates the necessity for algorithms that can learn step by step. Temporal difference, or TD learning, solves the episode termination bottleneck. It allows the agent to update its value estimates mid-flight, immediately after taking a single step. It achieves this through a concept called bootstrapping. This equation shows the core of TD learning. Instead of waiting for a final true return, the algorithm updates the current state's value based on the immediate reward it just received, plus the discounted estimated value of the next state. Together, the immediate reward and that next state estimate form what is called the TD target. The algorithm then compares this new TD target against its previous estimate for the state. The mathematical discrepancy between the two is defined as the TD error. The agent adjusts its internal map to minimize this error. Bootstrapping introduces a distinct trade-off. Because the agent is updating its knowledge based on a guess about the next state, it introduces initial bias. However, it drastically lowers the statistical variance compared to waiting for a highly unpredictable full Monte Carlo episode to finish. By utilizing the TD error, an agent learns dynamically and continuously. It can survive and adapt in stochastic environments without having to hit a terminal state to realize it made a mistake. Estimating the value of being in a particular state is useful, but it is insufficient for actual control. To optimize behavior, the math must shift to evaluating specific actions taken from those states, yielding an action value function. This introduces the exploration-exploitation dilemma. To discover the optimal policy, an agent must take calculated risks and explore suboptimal actions, which inevitably drags down its short-term performance.
Q-learning handles this dilemma using an off-policy architecture. Look at the Q-learning update rule. It calculates its TD target using the max operator. This means it evaluates the current state by assuming the agent will take the absolute best possible action in the future, regardless of what the agent is actually programmed to do next. This is what makes it off-policy. It learns the optimal policy completely independently of the exploratory, occasionally erratic, actions the agent is currently taking. SARSA, on the other hand, is an on-policy algorithm. Notice that SARSA drops the max operator. It calculates its target based on the exact action the agent actually plans to take next, evaluating the current behavior policy in real time, exploratory mistakes and all. This distinction matters in environments where exploration carries severe penalties. Consider micromanaging units in StarCraft. Q-learning's aggressive assumption that the agent will perfectly execute the next move can lead it dangerously close to enemy lines. SARSA acknowledges the agent's exploratory noise, leading to safer, more conservative routing. Engineers must evaluate their environment's tolerance for failure. They have to choose between the aggressive, independent optimization of Q-learning and the safe, policy-bound reality of SARSA. While Q-learning is foundational, it has a documented flaw when deployed in highly stochastic systems. It is highly susceptible to overestimation bias. Because the environment is noisy, the value of actions will naturally fluctuate. By continuously applying the max operator to noisy data samples, Q-learning systematically picks the positive outliers, artificially inflating the expected value over time. This mathematical quirk deceives the agent. It creates compounding errors, where the algorithm locks into incorrect, suboptimal policies simply because a noisy reward spiked once. To fix this, engineers deploy double Q-learning. This architecture splits the process. It maintains two separate value tables. It uses the first table strictly to select what it thinks is the best action, and uses the completely separate second table to evaluate the true value of that action. This decoupling breaks the overestimation loop. If the deployment requires on-policy control, engineers turn to expected SARSA. Expected SARSA abandons the absolute max operator entirely. Instead, it calculates the expected value of all possible next actions, weighting each one by the mathematical probability that the policy will actually select it. By decoupling estimators or weighting the probability of future actions, these advanced architectures correct for environmental noise. They translate pure theoretical algorithms into stable systems capable of managing real-world variance. There is no single universal algorithm in reinforcement learning. The architecture is strictly dictated by the constraints of the environment. If an exact transition model exists, you run model-based dynamic programming. If the model is missing, but the system allows for full, consequence-free episodes to finish, you sample data using Monte Carlo. If the environment is continuous and requires fast, step-by-step convergence without waiting for a terminal state, temporal difference bootstrapping becomes mandatory. Within temporal difference, if the goal is optimal learning independent of the agent's current exploration, you deploy Q-learning. If the environment is highly stochastic, you upgrade to double Q-learning to strip out the overestimation bias. Finally, if the system requires safe, policy-bound learning that respects severe exploration penalties, you deploy SARSA, or expected SARSA, to smooth out the variance. Understanding the specific limitations of each algorithm, whether it's the episode bottleneck of Monte Carlo or the positive bias of the max operator, prevents engineers from deploying mathematical structures that are destined to fail in their specific operational environment. Value-based methods provide the core architecture of reinforcement learning. They are the exact equations required to translate raw, unpredictable trial and error into rigorous, optimized autonomous behavior.